Students, welcome to Lecture 7. In today's lecture, we will continue our topic on event-related potentials and we'll discuss multivariate feature representations. The outline of today's lecture is as follows. First, we discuss about univariate features and how we can extend it to multivariate features. And then we talk about multivariate ERP model. So let's revisit the univariate feature representation of event-related potentials that we discussed in the previous lecture. Here, what we see is the multiple event-related potentials plotted in a superimposed form. All of them were collected from the CZ channel. We can see here two different classes of ERPs. So first one is target, second one is non-target, represented by blue and red colors. So univariate feature represents the point or single feature that has been collected in this specific example as amplitude features. Okay, so all these single features representing one ERP is called univariate feature. And the cross here represents the average of all univariate features for target class, while this blue cross represents the average of univariate features for all non-target ERPs. Well, constructing the feature vector is the first step in the BCI research if you want to train our classifier model. And we need to make some decisions on, for example, which time point we should select to extract or construct the univariate feature. Why 222nd millisecond? Or why not 300 millisecond? Okay, so in BCI, there are some decisions that we need to make in constructing the feature vector. However, for improved classification of EEG signal trials, we need to accumulate more information in the features. The univariate features may not be enough. Let me go back to this image example. Well, we can consider other feature vectors here as well. Not only at this 220 millisecond time point, but all the amplitude-related features from 200 to 300, for example. So the task is to expand this univariate into multivariate features or temporal features. And in addition, we're discussing only single channel. Okay? What about other channels? Can we also use them to construct more rich feature vector or feature vector set? So that will be the one of the main questions of this lecture. So let's give some formal names. So sample ERP signals at multiple time points or intervals, we call them as a temporal feature. Okay, those time points acquired from multiple intervals or segments of interval, we call them as a temporal feature. Okay? If, okay, there is a special feature we can define. So we're not only considering the ERP trials or EEG signal from single channel, CZ, but from all channels, from all possible or available channels, multiple channels. So there are two different types of feature we talk when it comes to EEG, ERP. Temporal feature, spatial feature. Temporal feature is related to time points, okay? Time. While spatial related to the space in the head, for example, which part of the scalp we are recording. Frontal, occipital, temporal, or parietal lobes. And we also can combine two features together, then construct the spatial temporal feature vector or matrix. Okay, so these are the terminologies used. Temporal feature related to time points, spatial related to channels, space. Both relate to spatial temporal feature. So when we extend from univariate to multivariate spatial features, we face some challenges. As mentioned before, we said that channels are highly correlated, right? So if we, for example, consider two channels, two channel recordings as shown here, one from CZ, another from OZ. Occipital central point, central. And our cognitive source, which is ERP, is well measured, localized in CZ channel. However, we have idle rhythm coming from the visual cortex, occipital lobe, okay, which is recorded by OZ. So if we want to record two channels and construct a feature vector, we need to take into account that there is some spatial mixing. And then the task is to demix, or extract the cognitive source of interest and filter out the background idle rhythm. For example, this is alpha rhythm. And eventually having the source, cognitive source related to ERP. So in these kind of examples, we use spatial filters for filtering the cognitive source. If we assume that our ERP is a constant, and this is, for example, represent as 1, okay, the amplitude 1, and we have some visual idle rhythm related amplitude value that is being added to the cognitive source, so 1 plus 1/2, okay? As the result, the visual idle rhythm changes the CZ acquired data. So here, if you see red and green region, so the univariate feature that we extracted from this time point is supposed to be here, okay, represented by this height of the amplitude. However, after adding this visual rhythm related noise, it will go down. So the original peak of the cognitive source is affected by noise, signal plus noise. And the task of the spatial filtering is to recover these through cognitive source by applying some weight to the univariate features, or multivariate later, okay? So for example, this is 1, this is another 1, if you assume, if you take it as an example, and half of the signal is attributed or affects the signal. Then the spatial filter for this specific example would be equal to 1 over minus 2 over 3, 4 over 3. So if we apply this weight, for example, W transpose X, where X is our noisy data, which combines cognitive source and visual idle rhythm, the spatial filter will work as a demixing. So in order to reconstruct the original signal, we just apply the weighting to each univariate feature, in this case CZ, OZ, okay? So it will be equal to the following coefficient or weights applied to each channel data or feature. And then we can reconstruct or recover the original 1, okay, which is the value of amplitude. Well, the advanced or multi cases in advanced problems that relate to volume conduction or spatial mixing is mixing of data from several channels, will also involve some kind of estimating the weight matrix, okay, that will decorrelate data from different channels. We will study those later. Another type of features that we commonly use are called temporal features. Okay, let's take same example. It's a cognitive source, visual idle rhythm. We take one univariate feature, which represents amplitude, right? And we know that the background idle rhythm adds up to the signal, 1 plus 1 over 2, and change the amplitude value. So this is not temporal feature, right? So temporal feature or filtering in simple case involves averaging, okay? Taking several univariate features and then performing averaging, and then recovering the original amplitude feature of the cognitive source, which will cancel out the background noise. So if I open up the slide from the previous lecture when we talked about averaging across trials, across temporal features based on the signal model that we constructed, where we assumed that the ERP is constant and we have some Gaussian noise. Then averaging will minimize the noise, temporal averaging will minimize the background noise, as in this case. So assuming that our cognitive source is constant, okay? So this is the effect of averaging, okay? Temporal feature, applying temporal feature. We also have some noise coming from DC drift, direct current related to electronic device equipment, which changes the baseline. Okay, so original cognitive source is usually has zero mean, but DC drift will apply this kind of drift. So we need to apply some kind of steps that will demean, remove the DC drift. Okay, we can take same univariate across different channels now, F3, FZ, F4, C3, CZ, and other channels. Select one time point, okay, at 200 milliseconds. These selected time points across different channels will be considered as spatial feature at some fixed time point. And we can visualize these features, spatial features, as topographic map, as I have already discussed in the previous lectures. Okay, what is done here, just take this amplitude value across these bigger, okay, these cross-represented locations of these sensors, and then perform interpolation. Okay, and represent amplitude values as color-coded. More red means this is microvolt, more higher amplitudes. More blue means more negative amplitudes. Okay, so we can see that CZ, which is located here, has higher amplitude values. And if you compare location of this electrode, so what could that be? So right hemisphere, even numbers. Left, odd numbers, right? And then this is central, frontal, parietal. Okay, so what would the value of this? So P3, parietal is the location. PZ, P4. This one C3, CZ, C4. F3, FZ, F4, and all other electrodes. And this kind of visualization can also be applied to not only amplitude values, but other distribution of power band or any other different representation of your feature vector. Power spectral density, wavelet coefficients, or any different representation is possible to visualize like this, even the weights of your classifier model. We can visualize the univariate features as histogram to analyze the distribution of the amplitudes across time points. So here, CZ, FPZ related data, EEG. Okay, and then we can map the amplitude values of single univariate feature across all these time points to the histogram, to represent as histogram. Okay, looks like it's similar to the bell shape, right? Normal distribution. This kind of visualization helps us to analyze further whether the data is being generated according to the assumed Gaussian or normal distribution, or some other interesting information like mean, skewed distribution or not skewed, or variance, and some other useful information about the univariate feature. Now we can extend the ERP model of the last lecture to the multivariate case. Here we have more than one channel. Okay, xk, k is a trial indicator of t at some time point, is equal to p potential from multiple channels. This is now a vector, and noise, some residual, right? So in probabilistic view, x and residual noise are both random variables over several trials, okay, from which we observe k many draws. And the noise, the residual is IID distributed for fixed t, as I said. And we assume that to be Gaussian, okay, Gaussian distribution, okay, denoted by zero mean and some variance, sigma. Since we assume p to be constant in each trial, this is a simplified assumption, we can easily deduce a distribution of x across several trials for fixed t, with mu, mean, and then variance. This is the covariance matrix already. For multivariate case, we are dealing with covariance matrix. In the diagonal, where diagonal entries represent the variance for each separate channel, okay? So this means that distribution of our x is distributed according to normal or Gaussian distribution. So if there is no noise in the data, the univariate distribution is usually close to Gaussian distribution. If you assume here the data coming from channel 1 and channel 2, let's assume that CZ, PZ, they usually approximate the normal or Gaussian distribution. With the mu, okay, get here mean and then some sigma spread. How about their joint multivariate distribution? What do they look like for given two channels? Right? We said that these channels, usually EEG channels, are highly correlated. So we are interested in multivariate distribution, how they look like. For that, we can take or show the example of two-dimensional Gaussians or Gaussian distributions. We may have two cases, correlated or uncorrelated, right? So let's take this component 1 and component 2 distribution and try to visualize their joint distributions. The correlated case usually have this linear trend, right? Linear tendency. So the univariate features, if they are highly correlated, we should observe the increase, okay, in the value of the univariate feature will also be highly dependent to the linear increase in the univariate coming from the second distribution. Well, uncorrelated case, we will have this kind of scatter plot. Okay. So two-dimensional Gaussian distribution for our data may have uncorrelated covariance diagonal matrix or correlated components, which can be decided from their marginal distributions of univariate components. So in ideal case, we want to have uncorrelated components, okay, which is what we want in the BCI. While correlation means they have a lot of common components mixing. This can be actually visualized by plotting two different channels, CZ and data from PZ, across different time points from 0 to 6 seconds. Okay, if we map these temporal features to this joint distribution, we see some linear trend. Okay, so they are highly correlated, right? And then task of the BCI sometimes is apply special filter to make them uncorrelated, okay, less correlated. That was one of the use case of special filters. In real world data, we're basically dealing with multivariate Gaussian distribution. Okay, so this is the Gaussian distribution for a multivariate case with, okay, some mean and then a covariance matrix and some normalizer. So this should be very familiar to you from your probability course. Most data will be assumed to be generated according to a Gaussian distribution. So let's talk about notions for constructing the feature vector and representing our data from EEG. Some of the notions that we can use are as follows. So XC at T represents a Scalp potential at channel C and time point T within a given trial, okay? So XC of T. While we can use this calligraphic C, capital C, to represent the feature that corresponds to a subset of channels. If you have M number of channels, we can represent them as follows, okay? As a subset or set. While here, we use the boldface X and then the subset of channels as C at T to represent the data vector for selected channels, okay, for M channels. This is one way to represent data vector from EEG, usually the amplitude values. And we have T, or calligraphic T, representing a temporal feature. So Ti, I range from 1 to I, which is the sequence of intervals, where Ti is a subset of indices, so subset, so temporal feature. Okay, so we will use these kind of notions to represent the feature vector for feature extraction. So please remember this. Based on the notions that we use for defining feature vectors, now we can talk about temporal feature vector construction or extraction of temporal features given data. For example, given a set of time intervals, okay, t, and one channel C1, we can define the temporal feature as follows. X at channel C1 and time interval that range from 1 to I, right? So we can construct this as mean values. Mean of here, the mean is taken across this given time interval defined by t to t1. And the dimensionality of the feature vector coincides with the number of sample points within one epoch. So one epoch means one time segment, trial data, one sample interval. So this is the location of the channels, okay? And then if we extract data from CZ, we can define temporal feature as follows. So one index, and then take the mean as a first feature, second and third, and so forth. We can construct the temporal feature vector as follows, and also visualize as a color-coded heat map for fixed channels CZ. How about spatial features? And how can we extract the spatial features from the given multi-channel EEG data? So let's define the set of channels as define C, calligraph C, and one time interval. So one time interval that can correspond to 100 milliseconds, okay, or 200 milliseconds. We define the spatial feature as follows. X at a set of channels and time interval. And this will give us the following vector. So we can take the mean, okay, at across time intervals. Here, this is set of channels, not single. And the dimensionality of the feature vector, spatial feature vector, coincides with the number of channels. We are performing averaging, taking the mean across time interval, so we're getting one value. And then each value of the feature vector is the average amplitude in one time interval of the respective channel. If we visualize some of the selected channels, AF7, AF8, CZ, OZ, and define our T1 as following time interval, okay, this could correspond to, again, 40 milliseconds. And then perform averaging. We will get one single value, which corresponds to the average amplitude in each channel. And we can visualize those average amplitudes as topomap, topographic representation, okay, through interpolation, where the color represents, again, the amplitude value. So defining temporal and spatial field features are the first step before feeding this set of features into the classifier to decode the user's mental state. So next set of features that we discussed briefly above is a combination of spatial and temporal features, as defined as spatial temporal feature. Okay, we define this spatial temporal feature as follows. So X, okay, is a vector or matrix of subset of channel C and in time interval. Okay, and our feature vector will consist of the following: the average across channels for the first time interval, second time interval, third, and I's time interval. Right, so each averaging across channels will represent spatial feature at T1, T2, T3 together will represent temporal feature. So we have feature from space and time. We can visualize them here as an example from a subset of selected channels: FC1, C2, C3, CZ, FC2, and OZ. And if you construct this spatial temporal feature, the matrix will look like this. So we have spatial relevant features, okay, and then temporal feature. This kind of information is, constructing this kind of spatial temporal feature is useful for analysis purpose. For example, we can pinpoint at CZ and time 175 millisecond, there is increase of amplitude. There is something going on, okay, at this time point, at this channel, at space and time. So spatial temporal visualization can also help. Okay, this is an example of a spatial temporal feature. Another representation is shown here. FC1, select one channel, different time points, average of different time points. Then this will correspond to temporal feature of FC1, temporal feature of FC2, C3, CZ. Okay, all together they will represent one tall vector. Okay, and we can, most of the time we visualize this spatial temporal distribution of the features as topographic maps, sculpt maps. So what is shown here is take this time point across several channels and visualize as follows, through interpolation. Second time interval, third time interval, fourth, okay, fifth, sixth, okay, sixth. There is some interesting activities going on, all red, right? All in most of the channels. And the last time point, right? Seventh time interval. So this kind of visualization usually helps to interpret the data that we recorded, right? And then probably to select a subset of the features for if you want to improve the classification accuracy of our BCI system. Now, what about the distribution of spatial, temporal, or joint spatial temporal features? We have seen in the previous slides that single trials of spatial temporal and even spatial temporal features can be visualized very well using sculpt topographies or analyzing the evolution of time courses or time amplitudes or some other sculpt map representation. And we have also seen that many of those features can also be visualized in the same way. But what about the distributions of the single trials or epochs as a scatter plot? Can we visualize as a scatter plots? How about the covariance matrices? We can definitely visualize the scatter plots of temporal features as follows. So we see some Gaussian-like distribution here. Each point corresponding to the temporal feature of a given ERP or segment of EEG, right? And then we have the mean average ERP or event-related potential. We can also visualize the scatter plot of spatial features similar to the temporal features as follows. Given each point representing the distribution of a sculpt feature or spatial features, right, corresponds to this one corresponds to the mean or average scatter plot. Okay, this kind of visualization also is very useful in analyzing your data. Let's wrap up the multivariate ERP feature representation. Here, what we see is the single trial data matrix from that represent ERP, color-coded. The amplitude values are color-coded. The range is from -100 to 800 millisecond from the following set of channels, okay, EEG channels. Then we said that if we select one channel, we can represent pure temporal feature in the following way, or we can also average indexes or subset of temporal feature. Okay, visualize like that. How about the spatial feature? If you select one time point across several channels, we said this will represent spatial feature at that time point. We can visualize in space. This is time, this is space. And finally, we talked about spatial temporal feature representation, where we have time and then space or channels. Okay, so time usually average across a predefined or fixed temporal index or interval. Okay, we can also visualize it using sculpt maps, those kind of spatial temporal features. So all of these examples of extracting, defining spatial or temporal features, or even joint spatial temporal feature, will be useful and very widely used in any part of brain data analysis, either for BCI, for decoding, or extracting meaningful information from the user's cognitive or mental state. So it is highly advised to become familiar with this kind of representation of the pure sinusoidal EEG signal. Okay, that gives us different insights. In the BCI classification cases, the distribution of ERP features that corresponds to different conditions are very important. We have to think about the distributions of features according to our model. The signal model, ERP, consists of the fixed potential, which is constant, it's not fixed, it's constant, and residual or noise according to IID distribution. If we assume that we have two conditions, condition 1 and 2, then both of the conditions will have different distributions. First condition could correspond to target ERP, second condition to non-target ERP. Okay, and then the noise is Gaussian. So we can visualize the distribution of target, non-target, select CZ and PO7 for ease of visualization in 2D, the scatter plot of a covariance matrix here, the region, and then the mean, which is represented by a cross. By looking at this, we see a lot of overlap in the distribution of two conditions, blue and red. But we also see that the mean of this distribution is different, which is already a good news. The remaining part is the noise, okay, which is captured in the variance of the data. In the future lectures, we will always be working with the EEG or ERP data generated according to some distribution based on our assumption. The task will be to classify them accurately into two different conditions. This is the end of today's lecture. We talked about moving from univariate into multivariate feature representation of EEG and ERP. We have also seen different ways to visualize temporal feature, spatial feature, or joint spatial temporal feature.